All right, everyone, let's take our seats. So our next speaker is from Microsoft. His name is Igor Zaika, and he's going to talk about Microsoft's approach to cross-platform development on Office. So without further ado, here is Igor.
Okay. Hello. Okay, you can see my slides, so that's fantastic. So hello, everyone. My name is Igor Zaika. So Kevin did an excellent job of pronouncing my name. So I came from Siberia, where it's very cold, much colder than in San Francisco. So I'm happy to be here for that reason as well. So I moved out from Siberia quite a while ago. So when I've got an invite from Facebook folks to come and talk here, I was actually interested in whether my talk and the things that I'm going to talk about are going to resonate with mobile developers, because if you think about Microsoft and specifically think about Office, it seems to be the opposite of what everyone has talked about today. But as I was listening through some of the talks today, I was actually surprised how we come to this from a completely different direction, because we are obviously not a startup by any measure. We have huge product, and I'll show you some of the statistics about our product. It's a big code base. And it's a very old code base as well. But we are coming to the same conclusions. We are using some of the same approaches. So here are the topics that I'm going to go through today. So first, I'm going to actually give you a brief history of Office, because some of you might be familiar with that, but some might not. And don't worry, it's not going to take a lot of time. And actually, the thing that I found surprising while preparing this is just how much of this history resonates with modern mobile development. A lot of the mistakes that we've made, a lot of the solutions that we found over those 30 years are completely 100% relevant. They're actually exactly what those talks today were about. So we'll go through that, and hopefully you're going to be as surprised and fascinated as I am. And then the next thing I'm going to talk about actually the state of the ecosystem, why Office is doing mobile, for example. None of that is going to be surprising, but the thing that is interesting is to look at all of the individual influencing factors that affect those ecosystems, and more specifically, all of the tensions that this generate. Because a lot of those factors are sort of self-contradictory and asking you to do two completely opposite things at the same time. And last, and I'll try to spend most of the time on this, is our actual technical strategy and what we do and how do we approach mobile development in Office. So brief history of Microsoft Office. It's 30 years old. It's actually just over 30 years old. So that's very old. Actually, there is a joke inside Office teams that our code base is old enough to buy its own alcohol and to have kids. In fact, most of the people, and I tried to do this calculation and didn't figure out how to get the data. Most of the people who work on a code base are younger than a code base. So most of the people were actually born after the first line was written. And the history looked like this. So it all started as individual apps in C, and we've actually lucked out that we've started in C and not anything else. And Microsoft Word for DOS has shipped at the end of 1983. And those two people were the key developers on Microsoft Word. So the guy on the left in the sunglasses, his name is Charles Simoni. I don't know whether you've heard about him or not, but he was one of the original developers of the Park Browser. And this was the first real WYSIWYG document editing system. So he left Xerox, he came to Microsoft. He was a dev manager for the Microsoft Word project. Another thing that is fascinating is that if you could read the letters on this screenshot, you would notice that Microsoft Word for DOS was developed on Unix. So I guess Charles Simoni liked Unix. And the last thing about him is that if you've ever heard about Hungarian notation, and you probably didn't, so that's a funny name, a way to name your variables that allows you to make non-type-safe C to be somewhat type-safe. And it leads to some interesting naming conventions in your code base. And then in 1985, Apple shipped Macintosh, and we've actually shipped Office applications on Macintosh. So we've started doing cross-platform development, not exactly mobile, it was desktop machines, but it was real cross-platform. There was very little similar between the DOS and Macintosh. So we've shipped that in 1985. And then came Windows. We've shipped on Windows as well. The thing that is fascinating when I was looking at the screenshot is Word 1.1 on a machine that had 1 megabyte of memory had half of this memory free after booting. And I wish our applications, even on mobile, were that small. So it's basically like roughly 256 for Windows, 256 for Word. And that was a full WYSIWYG editor with lots of bells and whistles. So 1990 was when Microsoft Office was born. So we've just bundled all of the applications together, called them Office. Virtually none of the code was shared between them. They were just individual apps with individual teams, but users loved it. So Office really started to pick up after that. So Office was successful in 1990. So what a lot of people, not all of them, but what a lot of teams do when they build a new product, it's been successful for a while in the market for 3 or 4 years, starting to dominate the marketplace, what do people do? So sometimes people decide that they need to rewrite everything because of course we've now been building it for a while. We are extremely smart, we are extremely successful. We are going to rewrite everything. It's going to be well architected because we know all of the faults with an existing system. It's going to have common code base. So that's actually interesting because a lot of that is going to resonate with the rest of the talk that can target Windows and Mac because we were starting to get tired with building multiple versions of the apps for Mac and Windows. And we went and actually did a lot of work for a fairly long period of time, more than a year. And what usually happens when you do that? Well, we've started to use C++ as well. But what happens is that usually projects like that do not succeed. Yes, we went for a while and we realized that what happens when you have a successful product and you try to rewrite it without really thinking about it too much, even with the best intentions, you forget all of the good things that the code base did and all of the good things that your users loved. So project was canceled. We had some really smart managers, but we did salvage a few things. So we've salvaged some of the architecture. We've actually managed to build a different product that could dual target to Windows and Mac. It was called Microsoft Word 6.0. And those charts, very old charts, so that's market share of different WYSIWYG processors, Word processors. So I don't know whether you've seen it, but basically Word 6.0 ended the competition. So not all of the other products died after that, but it really became dominant. It was an awesome product. It was very functional. It was fast. Users loved it. So we've dual targeted Mac and Windows. How did Mac Word 6 do? From the same code base, it didn't do nearly as well. Users did not actually like the fact that the product looked like Windows app running on Mac because we're so successful with making the same code run on both of the OSs. Actually, the performance was significantly worse. And when we were shipping it, it was already not a surprise for us, but it was probably a surprise for a lot of people. And it had a lot of reliability problems on a Mac that did not exist on Windows. So I'll actually go into details of this when I'll talk about some of the choices that we are making now based on some of those decisions. Lots of other things happened to your code base. Windows NT, Windows 95, we've moved to 32-bit, we've moved to Unicode. As you can imagine, for editing applications, both of those changes in the ecosystem were huge. They required significant redesign. Office 97 was a big release for us. We've made apps actually share code, because if you have apps that have toolbars and menus and dialogues, and you're using different technologies to do that, you're probably doing something wrong. So we've started to do this. We've started to use C++ at roughly the same time. It was C++ 98, so the Dropbox presentation had some of the types of code that we were writing. Actually, a lot of the code was still C compiled as C++. We've added COM, we added Visual Basic, lots of different features. And then there was an innovation of the decade. We've added Clippy. Actually, the teams that I am on right now, called Core Experience, we own most of the common user interface components in Office and the low-level application frameworks that they build this feature. We thought that it's going to completely revolutionize everything. So we talk about building features without really understanding the users first. But the quote actually says, "I see you are trying to take over the world. Can I help?" So other things help. This didn't necessarily do that. One notable thing that did not happen with Office 97 is we did not ship Office 97 for Mac. And the reason why we did not do that is we were so embarrassed by our 6.0 experience that we've decided that we're just not going to do the same thing. We are not going to have a code base where everything is so perfectly portable everywhere that it sucks in its own way. So what we've done instead is we've actually created a separate team that was completely focused on Mac. Part of this team is in Silicon Valley, part of this team in Redmond. So this team has complete freedom to optimize for Mac, both for performance and for Mac-appropriate user experience and application features. The product was called Mac Office 98. It was very successful. It actually, we've gained back some of the lost trust with our users. This product was important for Apple as well, because in 98, Apple did not do as well as it does right now. So it was actually very important that we've shipped for them, that we've shipped this product. But we've lost some things as well, because we've sort of over-indexed in a separate direction. We went from we can run everything from a single code base, from the single branch. Every developer actually had Mac and Windows machine. So we went into another extreme where we've shipped an excellent product, but we've lost a lot of the code sharing. And again, I'll talk later on what we are doing with that. So a lot of other things have happened. We added more apps. We added Visio, OneNote, Project, many other apps. Mac code base went through many different tool chains. GCC, Clang. We've redone our UI. We've decided that menus and toolbars and dialogues is too confusing to our users, given the complexity of the apps. We now use ribbons and side panes and dialogues because we had so many, it was difficult to get rid of them. And we've shipped Office for the web, so actual HTML apps that you can use in a browser. And we are on a version of 14 of the VC compiler by now. And we've killed Clippy. So that was innovation of the decade, number 2 with a single feature. So that was a lucky coincidence for us. So actually the email that went out when this change was checked in was amazing. What are we doing now? So the things that we are doing now is we have just shipped Office for iPad. I don't know whether you know that or not. It's a real Office product. It's actually using a lot of the code that goes into Win32 product. It's been very successful for us, and it was out for just over 3 months. We have, I think, 35 million downloads or something like that. And it was very well received, so users loved the quality of the experience. We've moved to modern C++, although the better description is we are moving to the modern C++ because we couldn't find a switch to just move our code base to the C++ 14. So we're just slowly going through this transition, but we are very determined because there are a lot of features that we actually like. And we are working on versions of Office for Android and WinRT, and I'll talk about some of the approaches that we are using for that. So how is this relevant to at scale? So it might already be apparent, it will become apparent later in the presentation, but a lot of the lessons that we've learned about cross-platform actually directly applies to what's going on with mobile right now. So we are going from a different direction. We have a huge product that was cross-platform in different ways for quite a long time. We have made some mistakes. It sounds like a lot of the mobile companies have made similar mistakes. We've learned things. It sounds like a lot of the mobile companies are learning those things now. And we need to be on a mobile. We need to be where our users are. So some of the things that we've learned from the history is that despite the fact that we've been doing as an industry cross-platform for quite a while, it's still hard. Not sharing code is bad. Sharing too much code, just as bad or even worse. Platform landscape is always changing, so something new comes up, something happens. So iOS was dominant, now Android is dominant. Who knows what is going to happen between those platforms? Platforms themselves evolve, so don't assume that things are static. And C and C++ actually worked out really well for us. And that's, for me, one of the more important takeaways looking back at the history. When I think back at what other language could we use that had the same combination of longevity, but at the same time evolution, I just don't know what that language would have been. Almost any choice that I can think of would have either been reinvented 1, 2, or 3 times, requiring us to rewrite everything, or would have been abandoned, requiring us to rewrite everything for a completely different reason. So it's an engineering conference. I'll actually show you some code before I go to more diagrams. So don't try to read it. I know that the font is too small, but the function on the left is actually a core editing function from Microsoft Word. It's taken from the version of the code from 1989. And the interesting thing about this function is, like, remember the Facebook presentation about immutable components and one-way notifications? That's how Charles Simoni designed Word from the start. So Word is actually based on immutable. The Word document is an immutable data structure. We actually never modify the character stream or all of the formatting. So all of the edits are done on top of this as revision changes. It cannot be objects because some of the objects will be too complex to update. So this code existed there from almost very beginning, so it injects something in the middle. On the right, the same function in Word right now. I actually took it out of the code base like a week ago. And the highlights is green is basically the same code. So we like this design. It's awesome design. It looks like a lot of people like similar design now. So we've been able to keep it because C++ survived all of this time. But on the other hand, if you look at all of the blue things, those things are very important as well. So the language used to be not type safe, so that's horrible. So now language is type safe, so we've changed that. We used to like global variables, so I'm not actually quite sure how Charles could be that smart about some of the design decisions, but still use global. Well, actually, I know exactly. The performance was so important that people were willing to sacrifice some of the niceties of the code for the performance sake. So we no longer do that, so we don't use global, so that's another blue. And security just wasn't as much of a concern back then. Now it is extremely important for us because we are an attack vector. So type safety, better componentization and structure of the code, and security. So this is really the only difference. So all of the good things we could keep, and all of the things that had to be evolved, actually the industry and us will manage to evolve. So I'll spend just a little bit of time talking about why we are talking about mobile, and that would sound very familiar given the presentations before. First of all, if you look around the room, everyone is using 2 or 3 devices. So that's just the reality of the world. It's just no longer a few people using mobile devices. Everyone is using a number of different devices. Those devices run different platforms, and that's the reality of the industry landscape. So we have to be where our users are. We have to be on Windows, on Apple, on Android, on the web, because if we don't, then we are not going to have sustainable business. Content fidelity is extremely important for us. So if you think about what Office is about your ability to author a document on one device, on one platform, and being able to display it perfectly on any other devices, and being able to edit it without ever corrupting your data. And we are looking for a market-leading experience. So we don't just want to be on all of those platforms. We actually want to be the best productivity apps on iOS. We want to be the best productivity apps on Android. And we want to be the best productivity apps on Windows. And that actually affects our choices in a very significant way. And we need to increase our velocity of innovation, because Office was always good at shipping on time, but we were good at shipping on time every 2 years, which is just not nearly fast enough in the modern world. Like 2 years, some of those companies that talked about amazing products today were created 2 or less years ago. So some of the influencing factors. So obviously there is Windows, Apple, Android, web. For a lot of the people in Europe, Apple and Android are probably the most important one, but web is pretty important as well. Windows has desktop. Each one of those guys have different APIs. So Microsoft has Win32 and WinRT. Apple has iOS and OS X. They're pretty similar, but not exactly similar. But then, somewhat orthogonal to that, there is a question of form factor, because you have phone that has one set of constraints of interaction. You have tablet, and then you have desktop, and then there are large screen, and then there is Apple Watch. So what if I wanted to project from a watch? Actually, wouldn't be that crazy of a scenario if you could make it work, but I'll probably not interact with it the same way I interact with tablet or even the phone. Different modalities of interaction as well: mouse and keyboard, touch, voice, gestures, compute. We used to do everything on the client. Now we do a lot of things in the cloud. There is much wider range of capabilities of devices because computers used to be very similar. Now they're extremely diverse. So those are influencing factor, and you can see that a lot of them just contradict each other. So they push you in different directions. So some of those tensions is you want to share code, but at the same time you want to have rich experience, and you cannot affect least common denominator. So you have to proactively fight that, because that's where any code sharing is going to push you, no matter how many times you're going to say, I will use native UI framework. Platform integration. You always want to use the latest and greatest features on the platform. That's just how it works, because that's what everyone is going to talk about. That's where users are going to go. So you need a very low-cost approach for how you can use platform-specific functionalities that just came out, and it cannot be expensive. But on the other hand, you need consistency of functionality. So when you differentiate between different platforms, you always take a risk that one platform is going to be significantly different from another. For Office, given our document-centric model, the complexity is that if we build features that actually go into content that are only available on one platform, users are not going to use it. We've tried it in a few places, and it just doesn't work. Unless it's present everywhere, you might as well not build a feature. Consistency of experience. So we need to make sure that our documents look completely perfect, and that all of the interaction with our servers are consistent as well between all of the platforms. And sometimes what it means for us is that we actually need to become OS developers. We need to take bits and pieces of OS code. For example, rendering is very important for us. So it might not be a crazy thing to say that we are going to just port all of the lower-level rendering code on all of the different platforms. And apps need to be consistent between themselves as well. So we want PowerPoint on iOS to clearly look like an iOS app. We want it to look like a Windows app on Windows. But at the same time, when users use PowerPoint on any of the devices, they have to understand that this is PowerPoint and not some other app. And release time and velocity of innovation is very important, because if you take too long between your releases, you're always going to have functional skew, and that's just not acceptable. So what is the solution? So we are here to talk about different solutions. So we've actually tried to put this question into all of the search engines that we know about. What would be an awesome, clean, architecturally sound solution for taking tens of millions of lines of code across several large apps that have been written over 30 years, supporting more than 1 billion users out there in the wild, and put them on multiple platforms and form factors, all with different API sets, and do that in a sound engineering way? And the answer was that, well, actually no one knows, and in fact we don't know either. But a few things that we do know is that there is no silver bullet solution. So there is no magic way to make this happen. We've tried a few different ones. They don't work. But there are approaches. If you understand your trade-offs and cost, risk, benefit trade-offs, then you can actually do quite well. And I'm going to talk about that in more detail in the rest of the presentation. So our cross-platform technical strategies. So what do we actually do? So yes, we start from a different from a different site. We already have a large code base, been on many different platforms before. Now we need to make sure that it's on all of the mobile devices, on all of the mobile form factors, on all of the platforms. How do we do that? Very difficult to describe all of the different dimensions that are involved in that. So instead of that, I'm just going to focus on three things. So one is working in a large code base, and we don't like to call it legacy. We actually like to call it legacy rich. I'll show you one example on how, if you use proper engineering approaches, you can actually make legacy code base to work with you, not against you. We believe that our applications have been very valuable for users for a long time, and if we do this work right, they will continue to be very valuable for the users on the new mobile devices. So second thing that I'm going to talk about is design and platform abstraction layers. So that's how you put boundaries between your shared C++ code and platform-specific functionalities, and what to do, what not to do. And then I'm going to talk about shading or not UX code and different trade-offs there. So So that was actually a test. So I just want to test whether anyone knows why I was showing this video. So I actually didn't even want to show this video. Instead of that, I wanted to show a completely different video. I wanted to show a video of an airplane that is getting rebuilt while it's flying, because it would have been a much better analogy of what we have to do. And actually, a lot of the people in the mobile community need to do as they evolve their apps. Because the things that we have is that we have a very complex code base. Even relatively new companies that grow very fast have very complex code base very quickly, and we just cannot stop the train and make big architectural changes, or, for example, put our applications on other platforms by stopping for a long period of time and then building something completely new and replacing it. We have to do something like in this video of a highway overpass getting replaced in Bellevue, Washington, where they very carefully constructed a new span of a bridge on a site without blocking any of the traffic. And then when it was ready, and they've tested, I hope that it was ready, they've blocked the traffic for a very short period of time and just added this new bridge span to already existing bridge. And they had a new, much wider bridge, much better designed, excellent seismic qualities, without actually stopping traffic for any significant point in time. So we have to do something very similar with our code bases. And when I say complex, like, it's always interesting to figure out how do you show complexity. And we've already seen some diagrams, I think, from Facebook with different arrows. So that's my arrow diagram. So again, I understand that no one is going to be able to read it, but what you see is actually the dependency graph of all of the build units that go into Microsoft Word. And this doesn't even include all of the shared code. So that's just a Word app. And it's not even interfaces and components. It's just an individual set of buildable components that are getting put together. And you might look at this and say that, OK, so clearly you guys are just not smart enough to build something simple and well-designed. So the thing that I would say is that, OK, so maybe half of that we were not smart to build something well-designed, but that's just the reality of complex software that has a lot of usage. So we need to know how to rebuild an airplane while flying. Otherwise, we're just not going to succeed. So how do we do that? So there isn't actually an agreement even inside Office on the best way to do that. Actually, a lot of people would advocate that we should do roughly what we've done with Mac Office 98, where we would just fork the code. So we have excellent source control system. So we'll just create a branch and we'll put a dedicated team into this branch and they will go off. And we actually have a proof that they're probably going to release an excellent product and it's probably can happen fast. And you know what you're getting. You know that you're going to have a team that is going to be single-minded. They're going to be focused on this product. They're going to be able to iterate fast. You know that they're going to be isolated from your main product. So you know that they're not going to break your Windows product or your Mac product in our case. But on the other hand, we know what happens because we have this 30-year-old history, because we know that it's only going to be fun for first couple of years. And then the third year is going to be a little bit less fun because you would realize that in order to merge in, pull in all of the changes that happened in the main trunk, you're now going to spend significant part of your engineering course just doing that. So we've decided that we're just not going to repeat that. We want to learn how to do everything in place. And the way we've approached that is we said that, well, the only way to do it in place is we actually need to figure out how to componentize our code base and build a set of components that can be composable with each other, so that we can reason over like what components should go into each platform-specific version of the app. So when we started to do that, we relied on a lot of the mechanical refactoring. And that's actually one place where C++ worked against us. Because C++ still is relatively weak when it comes to code analysis and refactoring tools. Inside Microsoft, we have a lot of tools that actually can do excellent code analysis, but they're all geared towards security. Because security is such a big priority for us that we've actually built all of this infrastructure. But we've never invested enough into making refactoring tools work really well for C++. We are super excited about what's going on with C-Lync and some of the tools that are now starting to come out. Places where we couldn't do mechanical refactoring, we heavily rely on unit tests. And I wish I could say that everything in Office is unit tested. I cannot say that. We do have a lot of code coverage. If you look at our code coverage for a legacy code base, it's very, very high, especially if you exclude all of the features at the periphery, because we have a lot of breadth, and then we have core that is highly used. Core that is highly used is actually has high degree of automation coverage, but not unit tests. And when you start building components, you absolutely need to do that. I'm probably preaching to the choir. But then we've done a couple of other interesting things that had big influence on how developers behaved. One is that we said that we are not going to allow pound if-def. So we just cannot do things like if-def iOS, if-def Android. You just don't do that in any of the code. And we do not allow any of the runtime checks. So you cannot do if iOS do this, if Windows do that, if Android do that. Because if you do this, you do not have portable code. So the amount of combinatorial complexity that you're going to have inside your code base is going to be so bad that you might actually be better off just having separate versions of the code. And we kept everything working at all times on all platforms. So Windows version, WinRT version, Android version, iOS version, all of them have to work at all times. Zero tolerance for any regressions of any automation, and zero tolerance of regressions of functionality. And we ensure this by doing very broad dog food. Microsoft is a big company. That's the advantage of a big company. You can actually just push software to all of the people. When you have this many people, you actually get quite a bit of usage by just doing that. This is the place where the legacy code base actually turned out to be an advantage, because when we started to do this, developers actually complained that it slows them down. They have to do too much work. They have to componentize, write unit tests. They need to do this and they need to do that. In reality, what it meant is that when they were doing work, they had to figure out all of the integration complexity up front. And that actually gave them all of the information that they need to do proper design and proper implementation. And it really played out well for us. So next slide, and next 2 minutes, we'll explain everything about the actual architecture that we use. So in a very gross oversimplification, this box in the middle is Office. And it consists of a few pieces. So the big box in the middle is all of the shared code. It's all C++, so no other language is used there because we just don't know of any other language that can be cross-compiled to all of the other platforms. Another reason why we try to keep this box as big as possible is content fidelity. The easiest way to have content fidelity everywhere is just use the same code to read, layout, render, do editing operations on all of the platforms. It's difficult because of the differences between the platforms, but if you achieve that, you know that you're never going to corrupt your documents, and that's a very important thing for us. So on top of that, we have service code. And again, you would think that Office is just a client application, but we actually do a lot of things in the cloud, not just with web apps, but with a lot of the collaboration scenarios. And we intend to push as much of the functionality into a service. We have to learn a lot about how to do this properly, but we already started to do that. We are going to do more, but we'll only do that where there is no expectation that the feature should work offline, because we are primarily an offline product. We believe that this is actually a big advantage. I can present in a room that sometimes has poor connectivity. Actually, I didn't even try to check what connectivity is because I was listening to the presentation. So on top of the big box of shared code, there is native UX. We actually just use native UI platform. There were a lot of discussions on, like, do you use HTML5 or do you use some intermediate layers or some custom UI frameworks? So I'll go into that in a little bit more detail, but we are firm believers that you need to use native UI frameworks. That's the only way to deliver best performance and best experience for users on a platform. But you need to keep this layer very narrow, and a lot of effort goes into that. And then at the bottom, there is a set of platform abstraction layers. So functionality in the OS that is different between different OSs, you need to abstract that. The fact that there is plural is actually very important. So we don't build one abstraction layer, we build multiple targeted abstraction layers. Often when you build features in a system like this, you need to work in all of the layers, and sometimes it's a downside, but we're just accepting that developers need to understand how to work in service, how to work in UI, how to work in shared. And it actually makes people learn more about the overall architecture of the product. So I think that the easiest way to talk about how successful we were with our approach is to look at the code sharing statistics. And those slides are actually from the PowerPoint architectural review 2 weeks ago. If you look at the WinRT version of the application, 96% of the code is shared code. So it's lines of code that identical lines compiled for WinRT, Android, Win32. So only 4% are unique. And those 4% are basically XAML files, because we build WinRT UI using XAML and UI-specific C++ code. If you exclude XAML, it's actually 98.6%. If you look at Android, 95% is shared, 5% is Java. And actually, when we looked at why it's higher than for Windows, we've learned a few things with our code gen tools that we generate for UI, where we generate code for UI bindings, where we just generate too much code. We think that we can make it even better. So again, it's cool if PowerPoint is just, I don't know, 1,000 lines of code. That wouldn't be interesting. It's actually tens of millions lines of code if you count code across all of the applications. That's why we care about those like 1% difference, because it makes a huge difference in engineering cost. So I'll jump into platform abstraction layer. So lots of history in the industry of how you do write once, run everywhere solutions. So Java, Flash, Silverlight, Pcode, HTML, 2 approaches push level of abstraction very low, so that you can just write a lot of code using the really low level APIs. Like if you can compile to something like machine code, even better. Or you make your API very broad, so that you can just live in this world. And we've actually done some of this. And we've hit a lot of the impedance mismatch. And impedance mismatch is an electrical engineering term, but it works amazingly well for software. And the best way to describe it is to actually describe what is impedance matching. Impedance matching is the practice of designing input impedance of the electrical load or output impedance of the corresponding signal to maximize power transfer or minimize signal reflection. And what it means for software specifically is that if you have a component that talks to an OS API and it pushes too much data to it, or makes calls too frequently, or uses it in a too complicated way, two things happen. Is either you blow up, so you don't have performance, you don't have the functionality or polish you need, or the OS blow up, and both of those are really bad. And actually, the Vert6 story is exactly that, because the Vert6 was just built on top of Win32 emulator. The people who've done this were extremely proud. So they thought that they've achieved amazing engineering feats by building this Win32 emulator, but they've hit all of the impedance mismatch problems. So user experience looked like Windows on Mac. Performance expectation mismatches are incredibly hard to deal with, because if you make very frequent call to OS APIs, even small differences in performance aggregate and make your application suck. And you cannot interop with any of the native UI. For example, if all of the UI is built using your own UI framework, you cannot embed any of the OS UI in yourself or yourself into the OS API. And you hit the least common denominator effect, because when developers find bugs that only repro on one platform, their first reaction is to actually limit the functionality so that they can avoid this bug by not doing something, because it's so difficult to get around them. So actual quotes from the Vert6 developers, there is actually a blog post on this that was published about 10 years ago. The only good thing about beating your head against the wall is that it feels good when you stop. This is direct reference to Vert6 experience. But when you do that, you actually learn how to do it a little bit better. And what we now do with platform abstraction layers is we only build them where we understand what our application needs to do. And it's amazing. Every time we do that, you think you understand your code base. Before you've done that, you don't. And we do not accept least common denominator. So we really need to understand how this is going to work on all of the platforms. And we are willing to sacrifice code sharing, and we are willing to redesign shared code in order to achieve better matching of the APIs. So the specific example of what we've done using this approach is composition and animation. So our documents are highly sophisticated custom rendering documents where we overlap a lot of objects with different effects. Everything can be animated. Obviously, it's editor, so everything is interactive. And with touch specifically, a lot of the touch interaction is basically real-time input and animations attached to it. So it's super critical for us that we do it really well. Very common solution to that, and we've actually done that on Windows, on Win32, on Windows 7 ourselves, is you just build all of that on top of OpenGL and DirectX. Those are very powerful APIs. You can do that. That's what OSs do anyway. So you just go and do everything ourselves. We had to do this on Windows 7 because it doesn't have a compositor API. So we've built all of this infrastructure. And what we found is that even on one platform, that's just so incredibly hard because you rely on different GPUs, different video drivers to have the right performance characteristics and the right reliability. And when something is as complex as OpenGL or DirectX, it's just very difficult to do that. Imagining that we'll be able to do that on iOS and Android and Windows, so it wasn't possible to imagine that. So what we have done instead is we actually took people who built all of this. So it was very important that those were the same people because they finally learned what we do. Because before we've done this work on Windows, we really did not understand how our applications work. And we've made them go and research core animation, research Android, and basically become deep experts on how composition, animations, touch interaction work on those. And we've learned a couple of things that are actually very common in other places as well. First is that people don't live in a vacuum. A lot of the subsystems in operating system are influenced by the same design trade-offs, so there were a lot of similarities. And we could actually see how we can build a set of interfaces that allow all of the compositing functionality. But we've as well learned that all of the OSs have performance and threading constraints that were completely opposite. So what core animation likes to do on the UI thread, you just won't be able to do on Android because it already does so much on the UI thread that if you do anything else at all, you're completely screwed. So you have to figure out how to do everything on another thread. And obviously on Win32 there is no animation and composition libraries at all. So what we've done is we've said, okay, so we're just going to go and design an API that abstract this out by making this API consist of async non-blocking APIs where we can reverse threading semantics in a way that is going to match all of the platform. And if you look at the diagram of how we actually composite all of our documents, so on the left is a big shaded block of C++ code, loads documents, does layout, and does rendering. On the right is our API that is completely shared. We use the same API on all of the other platforms to construct all of the layers and set up animations. And then there is a set of channels that go to different backends, and backends are different on different APIs. So custom backend on Win32, we use XAML on WinRT, we use core animation on iOS and OS X, and we use Android views on Android. But the most interesting thing is that if you look at the threading structure, so the green box is UI thread. The white box is what we call application thread. So actually, it's multiple threads. That's where most of the app runs. And the compositor thread. Application and UI thread are inversed on many of the platforms. So on Win32, we do everything on UI thread because that's just how Win32 apps work. On iOS, we do that because you can get away with that with core animation. It's a good API. And then on Android, we actually do everything on a background thread. And because we've used this async non-blocking API, we can completely reverse it, and all of the code would work. And if you go and play with our iOS APIs, with our iOS applications, you would actually see that the quality of experience is really awesome. We actually managed to nail our touch responsiveness and the quality of the experience goals. So those apps are actually really, really good. With XAML, we've used Android approach, not because XAML has the same problems as Android. It actually is better, but because we've already figured it out how to do this, it's just better to not do anything on a UI thread, because this way we can guarantee 60 GHz response. So I don't actually have time to talk about what we do with UI, but I'll just very quickly say that what we do is a combination of what Dropbox does and Facebook does. So you guys are smart. So that's the way to do it. So basically, what we do is we have an internal IDL that we use to define all of the components, and even the words are similar in some cases. And those components are fundamentally immutable components. So we use a subset of types that we can project into Java, that we can project in XAML, that we can project in into Objective-C. So the reason why I said that it's sort of a combination of it is it's both the boundary layer and it's the same mechanism that we've used for view models and models. And that's how we achieve the amount of the code sharing that you've seen. And to close, what I'll say is that really the most important thing is no silver bullets. Like if somebody comes to you and tells you that they have this wonderful technology, just use it and your mobile app is going to be awesome. Some messiah will show up at some point, but I doubt it's going to happen in the next 10 or 20 years. So really make sure that you understand all of the trade-offs and cost benefits and risks. Shared C++ core worked awesome for us, seemed to be working for everyone else. C++ 11 and C++ 14 is a much better language. And actually, there are relatively few downsides compared to other languages. So that worked well for us. I think it can work well for a lot of people. Use native UI frameworks. That's the way to achieve quality. If you design your app smart, the amount of code you actually need to write is very small. And like at the bottom, really think through the performance characteristic of your abstraction layers. Don't just try to build something like Win32 emulation, or like people have tried to build so many of those, I won't just be able to name them in 10 minutes. So that's the end of my talk. Thank you.
All right. Thank you, Igor. We actually don't have time for a Q&A, but we'll be back here at 4 o'clock sharp for our last and final talk on emerging Android. It's actually super awesome. So, I think we might have actually saved the best for last. But let's thank Igor again. I'm sure he's available for questions after the talk and at the happy hour.
Yep.
Maybe you'll get
I'll
more
be
frank
around, so
answers
if you
there.
have questions, stop by. I'll tell you more stories.
Thank you, Igor.